So here we go, continuing on with chapter 6. In section 4, we're building on the normal distributions we've looked at. We're going to touch on the central limit theorem. So some key concepts in chapter 4 in the section will introduce and apply the central limit theorem. The purpose of the central limit theorem is that it allows us to use a normal distribution for some very meaningful and important applications. We'll practice doing this and you'll see the importance of the central limit theorem. So in 6.4, we're going to talk a lot about X bar, or the sample mean. So to refresh you on this, we first looked at X bar in chapter 3. So we know X bar to be the mean of a set of sample values. So for instance, we could calculate X bar by taking the summation of all of the individual X values divided by the total number of X values that there are, or lowercase n, also known as our sample size. In the previous section in 6.3, we also covered sampling distribution of the sample mean, where here we had an entire population. We broke that population down into samples. We took the mean of all those individual samples, and then we ended up getting a population mean, or mu. So for the mean of all these individual samples, those were X bar values. So we had a whole population, or capital N, number of trials. From our whole population, we took lowercase n, number of trials, our sample size. Then we took the mean of those samples that made up our sample size of n. For example, if we had lowercase n equal to 5, then maybe our 5 numbers were 1, 1.2, 1.4, 1.4, and 1.6. We would take the mean of all 5 of those values. That is our sample number 1. That mean of those values would be an X bar value. So let's talk more about the central limit theorem and how it relates to X bar. So to define this, for all samples of the same size n, with n being greater than 30, the sampling distribution of X bar can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n, where n is the number of trials. So more on the central limit theorem for the sampling distribution, or X bar. In order to execute the central limit theorem, we need a population with any distribution. It can be normal, it can be skewed, it can be any other type of distribution. It doesn't necessarily have to be a normal distribution itself. So that population has a mean, or a mu, and a standard deviation of sigma. Remember the notation here. So mean for a population is mu, standard deviation for a population is lowercase sigma. Also, to execute the central limit theorem, simple random samples of all size n are selected from the population. So this is what we're used to seeing, where some sample size of n is taken from the population. It's important that these samples are randomly selected here. Now, I mentioned the distribution doesn't necessarily have to be a normal distribution. So what does that mean? We need to talk about the requirements for executing a central limit theorem. So the requirements are that either the population has a normal distribution, or n is greater than 30. So the number of samples is greater than 30. So in other words, we can use the central limit theorem if our population has a normal distribution, or if the number of samples is greater than 30. So if we check off one of these requirements, then these are true. So the mean of all values of X bar can be approximated as the population mean. We'll talk more about this notation. Also, the standard deviation of all values of X bar can be approximated as the standard deviation over the square root of the sample size. Then another concept we'll talk about again are our z-scores. So there'll be 2 different ways we can calculate a z-score within this section of the central limit theorem. Now, I mentioned how important these requirements are, right? So the population has to have a normal distribution already, or the sample size has to be greater than 30. So if the original population is not normally distributed and the number of samples is less than or equal to 30, then the distribution of X bar cannot be approximated well by a normal distribution. In other words, the methods of the section 6.4 do not apply. So if we're deciding if we're going to use the central limit theorem, we have to check off one of these requirements. If the setup of the problem does not fulfill one of these, then we can't use 6.4. Okay, so this will be really important, for example, when you have a list of questions and you're deciding which strategy to use. So if these requirements are not fulfilled, then you're not going to use the central limit theorem. If they are fulfilled, then we can use the central limit theorem. Next, we're going to talk more about all this notation here. So given our requirements in order to use the central limit theorem, where if all possible simple random samples of size n are selected from a population, where that population has a mean of mu, a standard deviation of sigma, then the mean of all sample means is denoted as mu subscript x bar, and the standard deviation of all sample means is denoted as sigma subscript x bar. So in other words, the mean of all values x bar, we can really denote that as mu sub x bar, where mu sub x bar is equal to mu, or the population mean. Then for standard deviation of all values of x bar, the standard deviation is denoted by sigma subscript x bar. That's really going to be equal to sigma, the standard deviation of the population, over the square root of the number of trials, or lowercase n. Now you may see this wording here as well. So sigma subscript x bar is called the standard error of the mean. So standard error of the mean, it's also sometimes denoted as SEM, so standard error of the mean. Let's continue talking through the strategy. We'll also definitely do examples of all this. So here's some considerations for practical problem solving. If you see some problem on a practice test or your homework or the exam, and you're trying to figure out, do I use the central limit theorem here? So point number one is you want to check those requirements. When working with the mean from a sample, verify that the normal distribution can be used by confirming that either the original population has a normal distribution or the sample size n is greater than 30. If one of these is not true, then we're not going to use the central limit theorem. So after considering this, does our data fulfill these requirements? We can also consider this. So we should evaluate, are we dealing with an individual value or a mean from a sample? Okay, so again, determine whether you are using a normal distribution with a single value of x or the mean x bar from a sample of n values. If you're working with one individual value, then we're going to use this version of calculating the z-score, which you've seen before now. So when working with an individual value from a normally distributed population, we're going to find the z-score by taking our x value minus the population mean over the population standard deviation. So we have seen this before in chapter 6. If, on the other hand, we're working with a mean or x bar from a sample of n values, instead, we're going to use this value for the standard deviation. So when we plug this in for the standard deviation, we're going to get z is equal to x bar now minus the population mean, or mu, over our definition of the standard deviation. To calculate the standard deviation, we're going to take the population standard deviation divided by the square root of the number of trials, or lowercase n. So they're very comparable, but we might need to first take sigma divided by the square root of n to then get our standard deviation here. We would do this if we're dealing with a mean from a sample of values, or we're dealing with an x bar value. If we're dealing with just a single x value, that's one data point, remember? And if we're dealing with an x bar value, it's because we took a whole population, or capital N number of trials, then from that population, we're taking just a small sample from the population, where we denote that sample size as lowercase n. Then if we find the mean of all those values in lowercase n, that's an x bar value. Okay, so keep these in mind as we're trying to figure out the z-score. You may need to take the standard deviation first divided by the square root of lowercase n. Let's start practicing this now and plugging in values. So the elevator in the car rental building at SFO Airport has a placard stating that the maximum capacity is 4,000 pounds, or 27 passengers, depending on how they estimated this value. If we assume that every one of the passengers weighs the same, then this converts to a mean passenger weight of 148 pounds. That is when the elevator is full. That's at capacity. We will assume a worst-case scenario in which the elevator is filled with 27 relatively larger adults. Let's assume the adults have weights that are normally distributed, that's an important part of the question, with a mean of 189 pounds and a standard deviation of 39 pounds. So in part A, find the probability that one randomly selected adult has a weight greater than 148 pounds. Part B, find the probability that a sample of 27 randomly selected adults has a mean weight greater than 148 pounds. Let's first solve this using Excel. So even before using Excel or the table, it's always good to draw out what scenario we're working with. So if we know that our data is normally distributed, and we want to figure out, does a randomly selected adult have a weight greater than 148 pounds? So to set this up, we would always draw our mean or mu as being right in the middle. Then our X value is our designated weight. So here it's 148 pounds. We're asked about the probability of an adult weighing more than 148 pounds. So therefore we need to shade in this area to the right of our X value. So this should look familiar. We're going to first use methods presented in previous sections. Why? Because we're dealing with just one individual weight. That individual weight, very importantly, is from a normally distributed population. And again, we seek this green shaded area here to the right of 148 pounds. In order to use Excel, we need to know our X value, we need to know our mean, we need to know our standard deviation, and we need to know the cumulative value. Because we're shading this area under the curve, either to the right or to the left, that cumulative value is a cumulative value of 1. But we need to remember that when we plug in these numbers into Excel, it's going to give us our cumulative area from the left. So once we get our answer using Excel, we won't be quite done with the question. So if I type this into Excel, equals sign, set up my function, I have my X value, mean, standard deviation, cumulative value. I hit enter, I get an area or probability value of 0.146565. Remembering what Excel and table A2 give us, it's the cumulative area from the left. So what do we need to do with this information? Well, because we wanted the cumulative area from the right, so to the right of 148 pounds, or probability greater than 148 pounds, we need to take 1, so the total area under the curve, minus 0.146565. When we do that, we get a probability or area value of 0.853435. That's the answer we want. That's the area to the right of our given X value. Now we're going to solve this using Excel and table A2. We're going to keep getting practice with both of those methods. So in using table A2, this is a special case because we first need to convert our X value into a Z-score. Remember, when figuring out which formula for Z-scores to use, we need to consider, is it a single X value or is it an X bar or a mean from a set of sample values? Well, here it's just one value of X. So we can use this version of the formula to get our Z-score. We need to know our X value, our population mean, and our population standard deviation. When we plug in all these numbers here, we get a Z-score of negative 1.05. So if we go to our table A2, we go to the negative Z-scores, we're going to find negative 1.0 on the left-hand column. Then for the hundreds place, it's a value of 5. So negative 1.05 for a Z-score. When we go to the table, we find that area corresponds to a value of 0.1469. We need to remember that both Excel and table A2 always give us that cumulative area from the left. So again, because we want this cumulative area from the right or to the right of our X value, we need to take 1 minus that value. So we get a final probability of 0.8531. Now, there may be some rounding using table A2, so really the result you get from Excel is slightly more accurate. Let's look at part B now. So find the probability that a sample of 27 randomly selected adults has a weight greater than 148 pounds. So now this is important to recognize. We're not just selecting one random adult from our population or from our sample. Instead, we're randomly selecting 27 adults. So this is really key terminology to look for when deciding, are we going to apply the central limit theorem or not? To really understand, can we use the central limit theorem, we need to check those requirements. So remember, we can use the normal distribution if the original population is normally distributed or our sample size of n is greater than 30. Well, 27 randomly selected adults, 27 is less than 30, so our sample size is not greater than 30. However, the original population of weights of adults has a normal distribution. We were told that in the question. So samples of any size will yield means that are normally distributed. So we check those requirements. Is our sample size n greater than 30? No, but we were told that our population is normally distributed. So because we checked off one of those requirements, we can use the central limit theorem. So let's figure out our notation here. So because we're now dealing with the distribution of sample means, we must follow these parameters. So we need to assign a mu sub x bar and a standard deviation sub x bar. Now for this terminology of a distribution of sample means, 27 would be our randomly selected adults. That distribution of those 27 randomly selected adults, that's what we're talking about. So we're dealing with the distribution of samples, of 27 random samples or adults here. And are really being asked, find the probability that that sample of 27 randomly selected adults has a weight greater than 148 pounds. So we're no longer dealing with just one individual adult. We're trying to consider all 27 randomly selected adults and figure out what mean that corresponds to. So that's the major concept from 6.4, this distribution of sample means. So we're basically finding the average of these 27 randomly selected adults and comparing this to our x value, or 148. It's sort of a unique way to think about this, but we can use these approximations now that we have checked off one of those requirements and we know we can use the central limit theorem. So for our notation, our mu sub x bar, that's really equal to the population mean, or 189. Then to solve for our standard deviation, or sigma sub x bar, that's really equal to sigma, the population standard deviation, divided by the square root of our number of trials. So let's go ahead and solve for that. We know our standard deviation was given as 39 pounds. The number of samples here we're working with, that's 27. So 39 over the square root of 27. Our standard deviation for our distribution of sample means is 7.51. And keep in mind why we might be doing this in the first place, because normal distributions are much easier to work with. We can equate the area under the curve to be equal to 1. That's a huge benefit because then we can find probability values that way. Also, if it's a standard normal distribution, our mean value is 0 and our standard deviation value is 1. If it's a non-standard normal distribution, that's okay too, because we know how to make non-standard normal distributions essentially converted into standard normal distributions. And remember, that's what we did in 6.2. So keep that in mind moving forward. This whole chapter is about normal distributions. And in order to answer sort of a unique question like this, one we haven't seen before, so the probability that a sample of 27 randomly selected adults has a mean weight greater than 148 pounds. We haven't really dealt with a question like that before. Normally, we're just considering one randomly selected adult. Okay, so just to clarify so far for part B, this question, we wanted to find the mean sub x bar and the standard deviation sub x bar. We did that by taking the population mean itself, or in this case, we need to take into account the number of trials n, so 27 adults. Now let's solve this and talk about how we use Excel. So before we use Excel, we want to draw a curve. Now to draw this curve is pretty interesting because we need to consider our mean value, or 189, and our standard deviation value of 7.51. Remember that the magnitude of the standard deviation value really shapes how that curve looks. So going back here to our original curve, we have a standard deviation value of 39. So here we have a standard deviation value of 7.51. That's a lot less than 39. So we're going to have a thinner distribution, a thinner shape to this curve. Okay, so we've checked off a couple things so far. We have our mean in place in the middle of this curve, of this distribution. We also know it's a little bit thinner of a distribution because it has a smaller standard deviation value compared to the population as a whole. So we have the shape to the curve, we have our mean, we have our standard deviation. Now, this is the tricky part here for the central limit theorem. So we're asked in part B about selecting 27 random adults and if they have a mean value that's greater than 148. So this is a really important part here. We're going to put 148, or x bar value, right here. Then our distribution is greater than that. It's to the right of that x value. Then because we want to know the mean of those 27 randomly selected adults, we're going to shade in this entire region here. Because we're asked in the question the probability of that mean being greater than 148. That's all we know. So any area here in the curve should be shaded because all of this probability is greater than 148. Okay, so in essence, we want to find the green shaded area in this curve. Again, one of the most important parts is figuring out where to place this x bar value. Now, before pressing play, I really want you to think about what you'd plug into Excel for a normal distribution function. What's our mean, our x value, standard deviation, what's our cumulative value? We sort of have to change the way we're thinking about this because we have our x value here that's to the left of this entire shaded region. When setting up Excel, this is still a normal distribution. We're told that that's part of the central limit theorem. So if we can use a normal distribution function in Excel, then for our x value, we have 148 pounds, so that's here. For our mean value, it's 189. It's what we figured out right here. So the mean value for the distribution of sample means is equivalent to the population mean, or mu. So that doesn't change. That's still 189. So extremely importantly here, we're not going to plug in our standard deviation of the population. Going back here to part A really quickly, our standard deviation of the population was sigma is equal to 39. We're not going to use that for part B. Instead, we're going to use a standard deviation value of 7.51. So now here so far, we have our x value, we have our mean, and we have our standard deviation value, where the mean and the standard deviation value are for our sample mean, or x bar, where the sample mean we're interested in is for those 27 randomly selected adults. Now for our cumulative value, we still want this full area to the left because right now we're just looking at 27 randomly selected adults with a mean value greater than 148. There's still a lot to this curve, a lot to our data that we're not looking at here directly in this representation of the data. So what we're going to do is plug in 1 here for our cumulative value. What is that going to give us? That's still going to give us this cumulative area to the left here of that value of x. The main things we need to make sure we did are using the proper x value, the proper mean, but that is equivalent to the population mean. But really importantly, the standard deviation value here has to be for the sample mean, not the population. So to get that, we took the population standard deviation divided by the square root of n. Then again, we use a cumulative value of 1. So we're finding this cumulative area to the left here. So everything to the left of this curve. When we hit enter, we're going to get a really small value, so 0.000 something 2. This is giving us our cumulative area to the left of the curve. We want this cumulative area to the right. So again, we're going to take 1 minus this small value to get our true value. Okay, so it's a little bit trickier how we think about this, but just stay organized. I really highly recommend you draw a picture like this to visualize everything. So using Excel, we used our x value. We also used our mean of all the values of x bar. For the standard deviation, we also use the standard deviation of all the values of x bar. Then we use our cumulative area of 1, because this is cumulative area to the left. We did 1 minus that answer to get our true answer. Now, remember when using table A2, what do we need in order to use table A2? Well, we need a z-score, right? So using table A2, using this x bar value of 148, we're going to calculate the z-score and then go to table A2. Now, why is this considered an x bar rather than just an x now? Well, it's because we're taking the mean value of all 27 randomly selected adults. Rather than just taking one adult and seeing if they have a weight greater than 148, right? We're taking a mean value of all those 27 randomly selected adults and getting a mean value from that sample. That's why we're using x bar here rather than just x. So to calculate our z-score, we really need to use the correct formula for our z-score. So to do this, we need our x bar value, we need our mean value, we need our standard deviation value, both for these sample means. So our x bar value is definitely 148. Our mean value, that's going to be the same for the population. And for our standard deviation value, we wanted to take the population standard deviation divided by the square root of n. So we've already done this, but I wanted to show this fully worked out. So 148 minus 189 divided by 39, or the population standard deviation, divided by the square root of n, or 27. We'd already done that previously, so here we're taking negative 41 over 7.51 to get our z-score of negative 5.46. Now, when you go to the table, you look for the negative z-scores, you try to find negative 5.46, you're not going to see that in table A2. So what do we do when we don't find our z-score on table A2? Well, there's something we need to remember for cases like this. So for a z-score of negative 5.46, I'll change this, it should be negative 5.46 here. We don't see that on table A2. So for any z values below negative 3.49, we use this assumed area of 0.0001. We use this for cumulative area from the left for z-scores up to negative 3.49. Keep this in mind whenever you have a very negative z-score. To be safe, you could use Excel instead of using table A2 for cases like this. So from this assumption, we have an area to the left, a cumulative area to the left of 0.0001, given this z-score that we had to calculate in order to use table A2. Now, with this value of the cumulative area from the left, we need to take 1 minus that value to get our true shaded region here, or the probability that we're interested in. So when we do this, we take 1 minus 0.0001, and we get a probability or area value to the right then of this specified x bar value as 0.9999. So with this probability value of 0.9999, that's almost 1. From that, we can say we are pretty certain that 27 randomly selected adults have a mean weight greater than 148 pounds, given the scenario, given the data we were working with in our question. So more on interpretation, in part A, we found there's a probability value of 0.8534 that an individual adult will weigh more than 148 pounds. Remember, part A was using one individual adult, so using X value instead of an X bar value. Then in part B, we found out there's a probability of 0.999998 that 27 randomly selected adults will have a mean weight more than 148 pounds. So with this information, given that the safe capacity of the elevator is 400 pounds, it's almost certain that it will be overweight if it's filled with these 27 randomly selected, relatively larger adults. The interpretation is important here because we can do the calculation, but we need to decide what does that calculation really mean for us practically. Now in Chapter 8, we'll get more into hypothesis testing, so a quick introduction here. When identifying significant results with probabilities, we again see this rare event rule for inferential statistics. That is, if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect, given that assumption, we conclude that the assumption is probably not correct. Again, we'll talk more about this in Chapter 8. Let's go through another example here with body temperatures. So assume the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, as is commonly believed for healthy adult humans. Also assume that the population standard deviation is 0.62 degrees Fahrenheit. It is important that these units match up here. If a sample size of n is equal to 106, if those samples are randomly selected, find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. So it should be clear from this wording that we have a sample from our population and we want to find the mean of that sample. This should indicate to you that I'm probably going to use the central limit theorem here. I first need to make sure these qualifications, these restrictions check out, and this sample size n is certainly greater than 30. We aren't told in the problem directly, is it a normal distribution or not, but we do have the sample size being greater than 30. So from that, we know we can use the central limit theorem. So this text here basically goes through what I just discussed. Feel free to read this. Because we're working with the central limit theorem, we should start to figure out our notation. So for our mean, or mu sub x bar, that's really equal to the population mean. And we're told in the question the population mean is 98.6. Now for our standard deviation for our sample mean, we want to take sigma for the population divided by the square root of n. Here, the standard deviation is 0.62 degrees Fahrenheit. Here, we're taking the square root of n, which we have 106 people that we're interested in taking their temperature for. Then here we get our new standard deviation value we'll work with as 0.0602197. Again, to clarify, we check those requirements. Does it either have a sample size greater than 30, or are we working with a normal distribution? Because one of those requirements checks out, we can use the central limit theorem. Then one of the first things we should do is figure out our mean value and our standard deviation value. After that, or maybe before that, we can always draw a picture. So if we draw this normal distribution, we know our mean value of 98.6. We also know our standard deviation value of about 0.06, but again, we're only drawing one distribution. So we're not comparing one distribution with a smaller standard deviation value to another distribution with a larger standard deviation value, for example. So we can keep our standard deviation value in mind. Let's keep drawing the picture here. So we're asked about taking the temperature for 106 adults, and if the mean of those 106 adults is less than 98.2, that means we draw our line here for our x bar value, and that's 98.2. So now we're pretty much all set. We have our x bar value, we have our new population value, we have our new standard deviation value that we're working with. We also drew this picture. We drew our line here, so we know we want the cumulative area from the left. So for the solution, I want you to plug this into Excel. In Excel, we're going to use the normal distribution function. So to set up a function, type in $sign and then norm.dist. We know our x value, we know our mean, we know our standard deviation. Importantly, we're using this mean and this standard deviation value that we figured out from this slide. Really, really importantly, we're using this standard deviation value, not the standard deviation value for the population. Instead, we took that value divided by the square root of n. So plugging these values in, knowing that we do want the cumulative area from the left, we use a cumulative value of 1. When you plug all this in, you'll get a value of 0 plus with Excel, or some very, very small number close to 0. Go ahead and use Excel, see what you get for this one. What about using table A2? Well, we know we need to convert our x bar value into a z-score before we can do anything else with table A2. So again, we have our formula here for a z-score for not an individual x value, but for a mean of a set of x values or a sample of x values. Plugging in what we know here, we already calculated these two. So x bar is 98.20 minus 98.6 divided by our standard deviation value. That's negative 6.64. Remembering what was mentioned on a couple slides ago, if we have a negative z-score of negative 6.64, that's a very, very small z-score, right? It's much less than 0. So when we try to find that in our table, we're not going to see it. Instead, we make the assumption that that area can be reported as 0.0001, as was done a couple slides ago. Remember, this is true for any z-score less than negative 3.49. Now, there's a similar thing for z-scores greater than positive 3.49. If you go to your textbook, you'll see a little indication that any z-score greater than positive 3.49, that area value, that probability value, can be assumed to be 0.9999. Okay, so we got our z-score. We had to calculate that first. We know that with such a small z-score, we can really think of that area as 0.0001. Because we do want this cumulative area from the left, that is our answer right there. 0.0001 is our area / our probability. Let's talk about the interpretation of all this. So the result shows that if the mean of our body temperatures is really 98.6, then there's an extremely small probability of getting a sample mean with 98.2 degrees Fahrenheit or lower when 106 subjects are randomly selected. Now, sort of interestingly, University of Maryland researchers did obtain such a sample mean, and they also confirmed that the sample is sound. Well, to explain this, there's two feasible explanations. One, the population mean really is 98.6 degrees Fahrenheit, and their sample represents a chance event that is extremely rare, right? We got a very small probability value from the question we just did. Or number two, the population mean is actually lower than the assumed value of 98.6. If so, then their sample findings are probably typical. Keep in mind we got a very, very small probability value, right? So because the probability is so low, it's more reasonable to conclude that the population mean is lower than 98.6. In reality, based on these findings from the University of Maryland, it appears that the true mean body temperature is closer to 98.2 degrees Fahrenheit. Definitely more studies would have to be done to confirm this. Okay, so I wanted to come back here again to reiterate how we found the standard deviation of all values of x bar. We did sigma, or the population standard deviation, divided by the square root of n, the number of trials. Now, there is a slightly different version for how we calculate the standard deviation value of sample means, or sigma sub x bar. The only time we need to do this, the only time we need to use this different version of sigma sub x bar is when we're sampling without replacement and the sample size n is greater than 5% of the finite population size, or capital N. In other words, if we took 0.05 or 5% of the number of subjects or the number of trials in our whole population, or capital N, we find that, and then our sample, our lowercase n, is actually greater than 5% of our total population. We find that, and then our sample, our lowercase n, is greater than 5% of the total number of values or samples in our population, then we need to do what's called a finite population correction factor. So essentially everything is the same from what we talked about in 6.4. Instead, though, we're going to use this formula for calculating the standard deviation of sample means. So you can see here, we'll take the square root of capital N, the total number of values or samples in our population, minus lowercase n, the number of trials in our given sample, all divided by, again, uppercase n minus 1. So keep in mind order of operations here. We do this top part, this numerator first, then the denominator. We would divide the numerator by the denominator, then take the square root of all of that to get our actual standard deviation value for these sample means when we have this qualification. Again, that's where lowercase n is actually greater than 5% of the number of samples or trials in our whole population. We had sort of these unique examples where we had safe loading of elevators, where we had a mean value, standard deviation value, and then an x value. We also had this example for body temperatures. We had a mean value, we had a standard deviation value, we had an x value. Now I want to point out one difference here. You may have recognized this. So the x bar value for the safe loading of elevators example, it was on the far left side of the distribution. So the x bar value wasn't even within the range of the distribution. While for the body temperature example, the X-bar value did fall in the range of the distribution. So I wanted to point out why that is. Why were these cases different like that? So again, here's our X-bar value. It's on the far left edge of the distribution. While for this example, we had the X-bar value that was within the range of the distribution itself. So the reason for this, we had a sample mean value denoted like this. So mu sub X bar was equal to 189. We had a sample standard deviation value, which was denoted like this. So sigma subscript X bar, that was equal to 7.51. Our X bar value of interest here was 148. So we have our mean value, we have a given standard deviation value, and we have an X bar value. Now, one thing we should ask ourselves is how many standard deviations away is this X bar value from the mean? From what we've seen previously in the semester, if this given value is within 1, 2, or 3 standard deviations away from the mean, it will be within the distribution itself. So let's answer this question. We'll take 189, the value of the mean, minus our X bar value of interest. That's 41. Now, how many standard deviations are within the number 41? So this difference between the mean and the X bar value. So basically the difference within this range here. Well, we take 41, this range here, divided by the standard deviation value of 7.51. That's telling us our X bar value is 5.4 standard deviations away from the mean. Because this X bar value was so many standard deviations from the mean, it's going to fall out of range of the distribution itself. Okay, so I wanted to point that out in case you're wondering, why is this X bar value not even within the distribution itself? So this is the reason. Let me know if you have any follow-up questions with this or anything else from any content we've gone over so far. We're at the end of 6.4 now. As always, let me know if you have any questions at all. Hopefully I'll see you in office hours soon. Have an excellent rest of your day.